much to organizers for inviting me. And usually I talk here in this crowd about sums of squares and moment problems, but currently I have other mathematical obsessions to pamper, and I'm very grateful to allow me to do so today. So I'm going to give you some ideas about my current mathematical obsessions. So let me say what it is about. So this is a very tall blackboard. So the plan of the talk, I'm first going to introduce the objects. And kind of give you the mathematical, a very, very short glimpse of the mathematical panorama where they appear, and then I will come to my main topic within this, and this is the notion of summability that I am struggling with for several years, but especially now. And I would like to illustrate this notion by highlighting several aspects of these constructions. Well, first of all, where it comes in introducing the algebraic structure on these fields of generalized power series, and then very quickly, without dwelling on it too much, I will talk about the analytic structure. Let me say that somewhere here already, a crucial tool that we use and that I would like to highlight here, because it's the only tool that I really know how to use right now, is a lemma by Bernhard Neumann that appeared in his paper on ordered division rings in the Transactions of the American Math Society a long time ago. I think it was end of the 50s. So that will have bearing on practically all the... So what I will do is that I will really sample situations and problems where this notion of summability is our monster versus our tool. So after the analytic structure, I will talk about introducing a different structure on those fields of generalized power series. I will tend to write those fields by the capital mass BBK. So I will introduce a different structure. More precisely, I would like in this context to tell you some thoughts about the Galois groups, the Galois group of these objects, and how we are attempting to investigate them. And finally, I hope to have time to also tell you about the differential structure. And with this, the aim of this, where summability comes in, is also to show you how these fields are very rich objects and what they can give us. So let me just define that, start with A. So what is that? So let little k be a field. Field here is commutative. I don't mean discrete field. Yeah. So I should say here that everything I do is commutative. Also, at the point where I appeal to my main tool, it is on ordered division rings, which was written for general rings, also non-commutative algebras. So let K be just any field and G be any totally ordered abelian group. So totally ordered abelian group, if not, I will write them additively since they are abelian, and I will mainly assume that G is not the trivial group, so they are automatically, it's easy to see that they are automatically torsion-free and therefore infinite. We're talking really about torsion-free infinite groups. This is because the total order is compatible with the addition, so you get that the multiples of a positive element already form a infinite sequence. So we are given those two objects, and what is this object? here. So this here is the set of all formal expressions of the form S is summation of S of G, T to the G. This is a formal expression where G ranks in G, and now comes some explanations. What do I mean by this? S of G is in the coefficient field, and we cannot just let G run where it wants. We must put the restriction that the support of S, that is the collection of G, for which S of G does not choose the zero coefficient, is a well-ordered subset of my ordered abelian group. And I remind you, well-ordered subset means that every non-empty subset has a least element, or if you want a sequential description of this, you can also say that it's an Artinian set if you want, if no infinite, strictly decreasing sequences in the order. Every strictly decreasing sequence is finite, so this is also a definition of well-ordered.
But this is a group, so it's this is kind of like a Laurent series. It's going both directions.
Yeah, well, you will see in a moment. The case where the group G is the simplest group, infinite group, the cyclic group,
Like the
Z,
integration.
then it's the Laurent series. We will see that. Indeed, as you say, in the case of the Laurent series, what are the well-ordered subset of Z? The well-ordered subset of Z can go only finitely many steps in the negative integers. So a Laurent series consists of a Laurent polynomial with a finite support plus a formal Laurent series.
So you
Yeah.
can only go
But
finite
this
many
is a
steps back.
generalization of this. Now, the Laurent series is a lot of the items 1, 2, 3, 4 that I wrote are very well understood for the field of Laurent series, but that is inherently so because the well-ordered subset of Z are of the form that I have just explained. However, the field of Laurent series is not enough for the purposes of real algebraic geometry or even of algebraic geometry, as I will explain in a moment, because the wildest groups possible can appear, and that's the beast we're trying to take. Okay? So on this set of formal objects, we define a pointwise addition. So I'm not going to dwell much more on the pointwise addition. The pointwise addition of these formal objects, so you take a formal object like this and another, and you just add the coefficients pointwise. And when you add the coefficients pointwise, you don't destroy anything with the supports, right? So at most, there could be cancellation. So at most, the support of the sum could be a subset of a well-ordered set, but the subset of a well-ordered set is still well-ordered. So pointwise addition of coefficients. And what are the little key examples that we favor? That I don't favor F2, but computer scientists do. These are strings of 0 and 1s. Fields of generalized power series are used a lot in automata theory. I don't know much about this, but I have a colleague who started by considering them algebraically and ended up having very much research in automata theory because they are used in recognizing languages and so on. But that's all what I'm saying about it here. These appear in computer science, in coding theory, and so on. But let me say that interesting cases also that appear are the field of real numbers as field of coefficient and the field of complex numbers. And more generally, K can be a so-called real closed field. So, or K can be an algebraically closed field in general. And there is a very famous commutative algebra evaluation theory work on this objects where I should mention many names, but very quickly without dwelling much on that. Saunders MacLean, Irving Kaplansky, Kohl, and many Hahn, and many others. But let me just say what I want to say here. If G is divisible, so if we take a divisible, totally ordered abelian group, then R double bracket G is real closed, and C double bracket G is algebraically closed. And moreover, I mean, you could also put here instead of R and C, I will stick to the classical fields R and C, but one could express this by saying if the field of coefficients is real closed, then the group is divisible, then the field of power series is real closed. If the field of coefficient is algebraically closed and G is divisible, then the field of power series will be algebraically closed. Here I'm expressing them just for R and C. And moreover, these are universal objects in the category of all real closed fields or algebraically closed fields, meaning that given a field K that is algebraically closed, you can find with a very precise procedure there exists a divisible totally determined by this algebraically closed field. There exists a divisible totally ordered abelian group G such that K has a representation, and there exists a divisible totally abelian group K, and a little field of coefficients that is algebraically closed as well, such that this algebraically closed field that is arbitrary has a representation in terms of power series expansions, right? I mean, not just one representation, many thousands. They are completely understood and classified. And similarly, given a real closed field, there exists a completely determined by this real closed field or divisible totally ordered abelian group, and a small real closed field K, such that the real closed field can be viewed as, again, as a subfield of a field of power series. So these are universal objects, and for the purpose of commutative algebra, this is the reason why we like them so much. But you see here, there exists a G. I'm saying there exists a G. Here now, just to give you somehow a feeling of where these mathematics are located, from my point of view, I just want to mention en passant that there is an absolute, so these are universal, but they are not absolutely universal, because you have to go and get this totally ordered abelian group G that fits to your given K. Now, if you don't want to care at all about getting the G, it's also possible. It's a completely masterfully construction that is due to John Conway, and that is the absolutely universal object, and this is the field no. He actually calls it no. He calls it no, the field of numbers, the field of Conway's serial numbers. And that is a universal, it is a field of power series, so how should I write it? No is actually R on double bracket, and it has this phenomenal property that the group of exponents that has to be taken here is again no itself. It has this phenomenal property, and it's a proper class. No is a proper class. It has to be because a proper class. It is not a set. I'm not getting into set theory, but it's not a set. It's a proper class. It has to be, since we are able to embed arbitrarily large real close fields in it, so it has to beat all cardinalities. Right. So that much about this amazing field of no, that actually it was written in the book of Conway as part 1 of a book called On Numbers and Games. And he used it very much in game theory later on, and I'm not going into this. Let me just say something about this field no, for those of you who know ordinal numbers. So the first, let's say just the first infinite ordinal number is the order type of the ordered set of natural numbers, right? So in this field no, you can, for example, perform things like, I would like to add the number pi to, let's say, 1 over omega. You can invert ordinals. So the field no contains the real numbers as a subfield, and the ring of ordinals, and the fraction field of the ring of ordinals. So this is where it is located, but I want to be much more precise. Really now totally focus, because I want to do some real algebraic, real algebra. I am going to just look at G, and there is an order, a total order. Well, you want to do real algebra, so you want real close fields, you want to consider a divisible group, totally ordered abelian group. From now on, without further mention, and RG, I want to also make it into a totally ordered field, otherwise why am I saying it's a real close field? Ordered field. And this you make as follows. You see, you take a series S, which is SG T to the G, and now this series, the G is a priori running in the group G, but in reality, it is running in this well-ordered subset, which is the support of S. Now, this is, being a well-ordered subset, has a first element. So let us define this. I will give this first element a notation. I will call it V of S, because it's actually a valuation that I will need later on. So V of S, I define it to be the smallest element which exists of the support of S, and that's how this will help me to determine the sign of a series S will be exactly the sign of the coefficient of S at its minimum of support. This coefficient has a sign in the real numbers, and that will be the sign, and that is the lexicographic order on that field, and it is easy to verify that it makes it into a totally ordered field that is real closed if G is divisible. You see why we need G divisible, of course. For example, the Laurent series field is certainly not real closed. You cannot take square root of T, right? Because square root of T would introduce an exponent 1/2, which is not there. Okay, so, hope I didn't get carried away. Not quite, but I started with 5 minutes delay. Okay, so I want to give just some examples of series, because if you've never seen series, it is not entirely useless to show you some concrete examples of series or of not series. So just very quickly, examples. So as Bill recognized, so example, the first and the guiding example that has, but it is unfortunately not at all purposes, let me write that L is the field of Laurent series. series. So this, in my notation, I want to say the real Laurent series since I decided to be real here. So this is R double bracket Z in my notation, and a typical Laurent series is a summation from I goes from M to infinity of Si t to the I, where M is some natural number, fixed integer, could be also negative, but only finitely many. So really a Laurent series, if you just restrict to the part, if that happens to be negative, from here to -1 Si t to the I, this is just a Laurent polynomial, and then you start again at 0. And this is a formal Laurent series in the classical. So this is a Laurent polynomial. And this is a formal Laurent series in the classical sense. Okay, so this is one basic example that one can look at, right? Now, not an example is this. This is not an example, right? Because of the decreasing supports. Another not example is if you do this you try to do this in again. If you do this, you cannot do this either, right? Because that violates all our definitions of this. Here it violates the well-orderedness of the support. Here it violates the condition on the coefficients. And I'm doing that, these are trivial examples, but I'm doing that on purpose because it will give you already the idea where the difficulties come with the notion of summability. You can, if you do that, so let's say if I goes from 1 to infinity and ranges over the natural numbers, you can, this is not a series because that would mean you're summing infinitely many natural numbers that doesn't exist in a field, right? So these are not non-examples, okay? Now I want to talk about examples which are no longer in the field with Z. So let us consider what happens with Q. So you see, Z has a very special property for as far as well-ordered sets are as far as well-ordered subsets are concerned. A well-ordered subset of Z is either finite or it's cofinite. It's unbounded. It has to go all the way, right? So it's either you have finitely many or you're doing all the big steps. You have order type omega u. But not so in Q. In Q, there are much more sophisticated well-ordered sets because you just, I don't know, let's say we go from -2 to -1 to 0 to 1. And here already, and so on and so on. And here you can already put in, here in this interval is a sequence of order type omega, right? Because you can take the sequence 1 minus 1 over I, where I ranges from 1 to infinity. You see, this is a strictly increasing sequence in this interval, but then you can continue and you can take as the next support 2 minus 1 over I, with I going from 1 to infinity, right? So now you are creating another strictly increasing sequence, and so on. So well-ordered, the possibilities of forming generalized power series with exponent group are much, much richer. In fact, if you know something about ordinals, all countable ordinals are embeddable in Q. The same order types that appear in Q appear in R. And for example, this series, summation n in n of S of n t to the g, so for a fixed g, minus 1 over n that I want to call S sub g, is a totally respectable series in that object, but also, so let me call this object here K, so this one is in K, but also I can concatenate these as I explained here. So, but also I could take all of these, one after the other, right? And let now G run here, G is fixed. This is that one here. But now I can concatenate all of these, and the sum total of their well-ordered supports will still give a well-ordered support. So series are much more complicated here. Now,
yeah, this is K, right? Not Q.
sorry?
The last element of K.
Yeah. Now this is already a wild object, even though the group, the divisible group here is one-dimensional, right? It's just divisible groups are Q vector spaces. Here the dimension is 1. But in general, you have divisible groups of arbitrary Q dimensions. So already here it's very complicated. But let me talk about the field of Puiseux series, which has been shown by Puiseux to be also an algebraically closed or a real closed field in the case you take real coefficients, algebraically closed in case you take complex coefficients. So this guy is really taking an increasing union of fields of Laurent series, really. So it is actually a Puiseux series. You put the condition on the, so it is still contained in RQ, so the exponents are still rational, but you put a condition on the exponents appearing in the series that they have a common denominator. A common denominator that is that M appearing here, right? This one. So I asked that the Puiseux series has a common denominator. So they are special series. They are the Puiseux series P, are those series with rational exponents for which the exponents, the support of S has a common denominator M. Fixed M is certain fixed common denominator. Now, if the support is finite, it's easy. Take the least common multiple or whatever, right? But if the support is infinite, in general, it is impossible to achieve a common denominator. So this is a real restriction. So the field of Puiseux series is a proper subfield of these guys. And it's much tamer, as I will show you when we do the summability issues, okay? Now I want to just finish this introductory part by another example, which is not an example, it's an observation. So, you know, if you have a totally ordered abelian group and a field of coefficients like the reals, the group algebra is a domain and you can form its field of fractions. So I want to tell you just to place things. So we could also do the group algebra. And how do we recognize the group algebra in the field of power series? It is exactly in the field of power series which have finite support with finite support. But this is just a subring, it is not a subfield, because if you want to invert those guys, you get automatically infinite support. Even if you invert 1 minus t, you get an infinite expansion. So the field of fractions of this group algebra are denoted by R1 bracket G, or the reals 1 bracket G, And just to be true to my abstract, I did say that there is an interesting connection between that field of fraction of the group algebra and the big field. It's not just that the field of fraction is sitting as a subfield, it's much more. And I am not going to write it, I'm just going to say it, just to place in the panorama. Every series in every power series can be pseudo-approximated by pseudo, because there is a pseudometric, the valuation is an ultrametric, right? It's not a metric, it's an ultrametric. Every power series can be approximated in the valuation by a series of rational series. Okay, this brings me into valuation theory too much, so I don't want to say much more about this. Instead, I now want to tell you I want to go to defining multiplication, because all of this time I have only told you what is the set and what is the addition, but to obtain a field I need a multiplication, and I need to show that for that multiplication non-zero elements are invertible. Okay, so I'm going to do that now. So what is the multiplication on these fields of generalized power series? So what is the multiplication? The multiplication, I'm going to define it like that. So this is putting some algebraic structure that I am here in my talk here. So what is the multiplication? So you take a series R and a series S that belong to K. K will be my generic writing unless otherwise for this guy, okay? If I want to make it more clear, I will write something else. So you take two guys here and you want to multiply them, right? You want a series. So how are you going to multiply them? So here is a proposal. I'm going to multiply them by saying, but the point is that the Cauchy product is absolutely non-problematic for Laurent, highly problematic otherwise, okay? So what is the Cauchy product? So I have to say what the product should do at a group, at an exponent, right? What the coefficient of a certain exponent should be. So I define it to be the summation. I let H run in G of the coefficient of the series at G minus H. G is fixed. For the purpose of this here, G is fixed and H runs, times S of H. So, in other words, my proposal is that the series RS, if I want to expand it as power series, I am writing it to be summation R G minus H S of H. Summation goes over G. This is G. This is G. And this is T to the G. This is my proposal for a product. It's a proposal. Now, you shouldn't like this proposal because it displays two problems. Do you see the problems? No? Okay, so the first problem, these are guys these are real numbers. This group is infinite. How can you, in the field of real numbers, have infinite sums? We're not doing analysis here. There is no conversions. Okay, so that's the first problem. And I claim I will show you that the imposition that we put on the supports being well ordered, I will show you that this sum is actually not infinite, it's finite. I will show in a second. That's the first problem, but the second problem is that even if you won that game, even if you were able to show that this sum is finite, who tells you that the support of the product is still well ordered? Otherwise, you're out of your field of series. So there are two problems here, and these problems lead me to the notion of summability of series. So summability. So the problem of summability comes now finally. So here is the problem. Consider a family indexed by some index set, infinite family. In this case, there is nothing to do. Infinite family of elements of K. Okay, so I will just enumerate this family, index it as I in I is some infinite index set. Just some infinite index set. So this is a family, every Si is a series in K, and what I want to do is to make sense in K, make sense, so the goal is make sense, whatever makes sense means, I will give it a precise definition in a second, make sense of summation I in I of Si as an element in K. You will see in a moment it's not always possible to make sense of this, right? For example, the two examples I gave you in the beginning, I gave them for that purpose. The example of t to the minus n and the example of nt, right, do not make sense. Every individual member makes sense. T to the minus n is a monomial, but the fact indexed by the natural numbers doesn't make sense. Similarly here, nt is a monomial. I mean, it's a non-monic monomial, but the sum doesn't make sense. Here we ruin the supports, here we ruin the coefficient. So it's not always going to make sense, and that's a challenge. So now definition, we say it makes sense. We say that f is summable So this is the notion of summability that is the official meaning of making sense if two things happen. If first of all, when we take the union, which I call with a big S, big support, the union of the support of Si for all I appearing, this union should still be well ordered. This is number one. So this doesn't wreck the supports. And number two, we don't wreck the coefficients. So for every G in G, the set of contributions with a coefficient, the set S sub G, so the set of contributions means I am a sequence in my family contribute at that spot. This set S, which is the set of all indices for which G is in the support of Si, this set has to be finite for all G. Okay, so this has to be well ordered, this has to be finite, and note that if F is summable, then it's obvious how to define, we wanted to make sense of this, how to define this, right? It's obvious, because now we can do it. We just define it to be equal to summation. Now G goes in this nicely well-ordered set, support F, right? And the coefficients come from this nicely finite set. This is going to be the coefficient of T to the G. Okay? So that series makes sense, yeah? Oh, I have 5 minutes? Oh, wow. Okay, so in this we can show that multiplication is well defined, and summability, you have to choose a certain family that has a summability property. It is the family of just multiplying by monomials. But I will omit this because I really want to talk to you about Neumann lemma, which gives us a complete tool for handling summability. So Neumann's lemma says the following. Now, if S is a series that I will call epsilon because there is a special condition on it. So if epsilon is a series such that the support of epsilon, so now comes a condition of positivity, the support of epsilon is completely positive. So, by the way, it's enough to say that the minimum of the support of epsilon is positive. For these, all power series powers of epsilon, and you can decorate them with real coefficients if you want. You can decorate them with some real coefficient AI. All of these, for no matter choice, is summable. I mean, the family is summable and you can make sense of this, but there is that very grave restriction about the support being completely positive. So in particular here with this Neumann's lemma, you get to show that this is a field because you can find the multiplicative inverse of something like 1 minus epsilon, which is epsilon I 0 to infinity. Okay, and from this inverting things of this form, you can invert any series because you pull the monomial of least degree. This one you can invert in the group because t to the g has an inverse t to the minus g. You pull the coefficients that goes with it. This one you can invert because it's a real number. And then you invert the remaining. You decompose your series into these 3 terms. Okay, now Neumann's lemma allows us to define analytic structures on those fields, which was going to be that, but you can ask me in the remaining 15 minutes about the analytic structure. This has been studied a lot in generalizing Tarski transfer principle from just the ordered field of real numbers to the ordered field of real numbers with other functions, such as the exponential function, sine, cosine, restricted to the unit interval, and things like that. So that has created all this O-minimal geometry, and that's yet another story that I don't want to say here, but I want to at least tell you a few words about the difference and the differential structures. You tell me when I'm in minus time.
Okay. 3 minutes.
Okay. So I want to tell you about the difference and the differential structure. So the difference. So difference means we want to study the automorphism group under composition, right, of this object. Now, I actually want, because I'm doing real algebra here, the order-preserving field automorphisms of this object, right? Now, the field of real numbers is sitting in there. The only order-preserving field automorphism of an Archimedean field, in particular R, is the identity. So this is actually the Galois group over R. So in wanting to study this, this is the session that I have currently. I am supervising one of my PhD students on that, and that's why it's so much in my mind. When we want to study this, there are two important maps that relate the automorphism group of K of the field of power series to the automorphism group of its exponent group. So actually a lot is reduced to automorphism of ordered abelian groups, right? I don't have time to define the maps, but the maps give us two important subgroups. One is called the normal subgroup of internal automorphisms. The internal automorphisms are those automorphisms that do nothing to the exponent group. I mean, they induce the identity, but they are non-trivial automorphisms. On the reals, on the coefficients, nothing will happen anyway. And the external automorphisms are the other extreme. The external automorphisms are those that you really obtain from moving by an automorphism, a shift map, right? Okay. So I want to just close. Unfortunately, I totally ran out of time, but I just want to close by saying something about this automorphism. So there is, when we study those automorphism groups, we strongly prefer to work with strong automorphisms. Strongly linear automorphisms. So what is a strongly linear automorphism? It's an automorphism that when you apply, that is strongly linear. You apply it to a series, input the series, output, well, you do nothing to the coefficients because it's a Galois group over R, and here you get sigma t to the g. This is the definition. If it satisfies that equality, it's the definition of a strongly linear automorphism. Now, strongly linear automorphism have to do with summability, because if you look at this equation, this is telling you two things. It's telling you that the family sigma of t to the g, with g in the support S, is summable. Otherwise, it wouldn't make sense to write it down, right? But it's also telling you not only is it summable, but the guy it gives is precisely equal to sigma of S, two conditions. So I wanted to dwell a little bit more, but I'm out of time now. So the thing I wanted to tell you is that the work of Schilling completely analyzes the automorphism group of the field of Laurent series, and the beauty there is that there is a simple argument to show that every automorphism is strongly linear. And one can generalize this argument to the field of Puiseux series, and I wanted to put an open question for the general case, and thank you for your patience.
Let's take a break now, and questions we can ask offline. That's okay, so we have 7 minutes. I'm abiding by the 7-minute rule. Come back at 3.
So for the Laurent series, what Schilling does is he shows that everything is strongly linear.
Yeah.
I mean, he doesn't say it this way. So
That's what you said, yeah.
yeah,
right.
so sigma in automorphism of the Laurent series is automatically strongly linear. And it is not too hard to prove it for the Puiseux